Okay, the next talk is by Valery Suleimanov, who will repeat the okay, and who will talk about accretion heated atmospheres of X-ray bursts in neutron stars.
So, good morning, everyone. It seems that X-ray bursting neutron stars is well-known objects, and it's not possible to say something new about them, but I will try. Why it's important? Because it's X-ray bursting neutron stars give us a good possibility to measure neutron star radii. It's important for establish equation of state of neutron star matter in the cores. And most of the facts is here. You can see duration of the burst about between 10 and 1,000 seconds for typical one. And here it's light curve of typical X-ray burst with photospheric radius expansion. Here it's burst is not stopping, but emission is go to ultraviolet region out of the observed band in X-rays due to strong expansion of the photosphere and temperature decreasing. This is typical phases of X-ray burst. Initial phase when burst start, and then expansion bands phase for photospheric radius expansion bursts, and then cooling phase. So, and here in the light curve, temperature changing and normalization changing using blackbody approximation of the spectra are shown here. And all three phases are shown also here on these curves. And most important point for us is touchdown point, so-called touchdown point where temperature has maximum value and normalization is the smallest value. It's clear from the common sense that in this cooling phase, the physical radius of the neutron stars cannot change. But what we see here, we see that normalization or blackbody radius of the neutron star change during this phase. Why? It's not observed for all X-ray bursts, but only for the part of them. But it's important to find neutron star radii using this fact. It's arise due to some features of the observed spectra and theoretical spectra of hot neutron stars. You see here that model spectrum of the hot neutron star atmospheres is very close to diluted blackbody due to strong interaction between electrons and photons due to strong Compton effect. But its shape, it's very good blackbody, but shifted corresponding to blackbody with effective temperature to higher energies. And if we feed this spectrum with blackbody, we will see that it's diluted. It's formula for this approximation of the theoretical spectra, and we see that this blackbody with temperature higher than effective temperature. I would like to remember that effective temperature means that this bolometric luminosity is the same for this theoretical spectrum and this blackbody spectrum. Okay, and we see that there are two parameters for this fitting: color correction, which shift the maximum of the spectrum to the highest energies, and dilution factor, which depress this blackbody up to model spectrum. And if we will see how we approximate the observed spectrum with blackbody, we see that this blackbody connected with effective temperature through color correction and through gravitational redshift. And it's clear that this normalization could change only due to this dilution factor. You see this normalization change during this third phase when we believe that physical Newton's star radius is not changed. And here in normalization you see that gravitational redshift cannot change, physical radius of the Newton's star cannot change, distance cannot change. Therefore, any changing of this normalization arises due to this dilution factor. And it's possible to compute how this dilution factor and color correction factor depends on the relative luminosity, relative to Eddington luminosity. I mean, its color correction factor has maximum at largest luminosities and then decrease with luminosity. And dilution factor has minimum at high luminosities and increase with luminosity decreasing. What we can observe in comparison with these theoretical curves, it's possible, in fact, to fit the observed curves. Here is bolometric flux and here is normalization. It's possible to fit by theoretical curves. But this fitting is possible only for system when X-ray bursts happen in hard quiescent spectral state. And you see here for this ultra-compact system, two spectral states in quiescence. It's soft and spectral states, persistent emission, and this hard persistent spectrum. And we believe these two cases corresponds to different physical pictures. Optically thick boundary layer for the soft state and some rarefied high temperature accretion flow for the hard persistent state. And we know that observed curves corresponds to theoretical curves only during only for burst, which happens in hard persistent state. Here you see two examples for two different sources, and you see that if persistent flux is much more smaller than Eddington flux, or 2%, the deviation is not so high between theoretical and model curves. But if we see in another system, it's very famous ultra-compact system with period close to 12 minutes. We see that deviation starts much earlier than here, and it's much larger in amplitude. Persistent flux here is about 7% of Eddington flux. Therefore, we see that there is some correlation between deviation of model curve from observations on persistent flux. And we try to explain it using this picture. Here we see that some accretion can continue during the burst, and this hot accretion flux can continue to accrete for neutron stars during the burst too. And I believe that we see this deviation due to this additional heating of neutron star atmospheres due to fast particles which accrete on the neutron star atmosphere. The qualitative picture is here. So plane parallel atmosphere is heated by a flux of fast particles. It's not hydrodynamical picture, but we have to consider every particle as separate particle which penetrate to atmosphere and lost his energy, release energy. And there are some additional parameters to describe this task. Velocity of accretions, accreted particles, angle of this direction of this velocity, and then we have to know that protons and ions in this hot accretion flow could have temperature close to virial temperature. It's very high temperature, up to 10 to 12 Kelvin. And we have to take into account some distribution of the particles in the space and in the velocity space. Particles penetrate up to few Thomson optical depths and column density of between 10 and 1 grams per square centimeters. And additional parameter is this accretion luminosity, which rise in this relatively thin skin of the above the atmosphere. And local mass accretion rate could be found from this using these parameters. Short history. This picture was considered many times. The first by Zeldovich and Shakura in 1979, and they shown that energy release will be in the optical depths parts of the atmosphere. And Larkin gave us the correct physical picture how a fast particle lost his energy in the plasma due to Coulomb interactions. And this works was the first correct computation of this accretion heated neutron star atmospheres. And here our Italian colleagues gave good contribution in the problem, and postgraduate students of Henrik Spruit gave us some application to try to explain hard persistent spectra of low mass auxiliary binary using this physical picture. And we developed our own code, which based on the same code which we compute non-disturbed neutron star atmospheres, and we add some additional energy release in the upper layers, additional force, ramp pressure force in the atmosphere, and take into account electron thermal conductivity. In this formula from Larkin, it's some only main terms, and some results which we obtained using this approach. Of course, there are a lot of parameters. Unfortunately, first of all, it's input. All computations was performed for these parameters of neutron stars, and it's internal some burst luminosity and free fall velocity here, virial temperatures here, and some parameters for accretion flow. Accretion luminosity, it's relative to Eddington. Some parameters which characterized velocity of particles in comparison with free fall velocity, sorry. And here is some parameter which correspond to temperature to virial temperature and angle of the penetrating. And of course, we consider different chemical composition of the accreting matter and atmospheres. That's some example of the computations. You see here it's a spectrum, and it's not flux, but energetic flux. Energy of photons multiplied to flux, nu if nu, so-called. And you see that it's possible to obtain very flat spectra with typical depressions here. It's exponential cutoff. I mean, and you see here's temperature structure of the model atmospheres. And I would like to say with some honesty that our code could give good results and allow to solve radiation transfer where temperature change in 2 orders of the value of the magnitude in very narrow region. And some other interesting things that angular distribution of the emergent radiation, it's a little bit strange, but it's expected that it could be like this. We can see lamp darkening in these relatively low energies, and limb brightening in these relatively high energies. How to expect? Because in this hard radiation rises in this optically some hot upper limb layers, and of course when we see in some larger angle, we see more and more energy which come. It's optical depth of the layers becomes larger, and we see larger intensity here. Of course, if relative accretion luminosity becomes smaller in comparison with internal luminosity of the atmosphere, deviation of the spectra becomes smaller and smaller. And here you see that for models close to Eddington limit, the deviation is very small, and the same for temperatures. The same, it's possible to say when we decrease accretion luminosity. In this case, the deviations decrease too, spectra from the spectra of undisturbed model atmosphere. And a very interesting thing connected with solar abundance atmospheres, because in undisturbed model atmospheres we see some absorption edge for hydrogen-like iron. And why is this edge rise? Because opacity here is much larger than here. Therefore, spectrum here rise in upper layers with small temperatures, and therefore we see some depression in the flux. So here flux rise in this part of the atmosphere, and before edge here in more hotter layers of the atmosphere. That is the reason why we see some edge. In heated atmospheres, you cannot see any edge. It's disappeared because all of part of the spectrum, this part and this part, arise in the same geometrical and physical part of the atmosphere here with the same temperature, and the edge disappeared. Using this approach and some parameters, we computed these curves only for one log G, of course, unfortunately. For helium, pure helium model atmospheres, and you see that heated model atmospheres give a little bit larger color correction, a little bit smaller dilution factors, and less prominent changing at high luminosities. But the most interesting thing connected with solar composition atmospheres, because in models with solar chemical composition, we predicted some deep depression at relatively low luminosities, about 0.1 Eddington luminosity, due to existing of this edge. You see that in heated atmospheres you don't see any depression here in this luminosities, and therefore our models predict that any features connected with absorption edges have to be disappeared if additional heating in atmospheres, if accretion take place in during the end phases of the burst. And it's possible to compare our results with observations. The first of one for helium accreted atmospheres. It's in ultra-compact object with this title. We believe that it's almost completely helium accreting system. And you see that with the same fitting parameters, our heated curve gives very good description for low luminosity part of this observed curve, normalization versus volumetric flux. And this part of the observed curves described by undisturbed theoretical curve. And there is some transition part the transition part of the luminosities when something happens, transition between unaccreted situation to accreting systems. And almost the last slide, it's not our result, but our colleagues from Canada. Andrew Kamek is the leading scientist of this investigation. They showed that observed curves, here it's k to minus 1/1 it's to describe not dilution factor but color correction factor. And it's some theoretical curves here, it's this logarithmic scale. There are some hard evidence, so strong evidence that this cloaked buster accrete solar composition, matter with solar composition, and for metals too, and we expect this kind of curves. Instead of that, we see this fast increasing of the color correction without any depression, and it was some problem which, to be honest, was clear why it's reason, and now we can at least qualitatively describe this kind of observed curves, and therefore we believe that all of the observed curve normalization, blackbody normalization versus blackbody flux, bolometric flux, could be explained by accretion of material on the neutron star atmospheres in the late phases of X-ray bursts. And this is my conclusions. Thank you. They are Raman.
Thank you, Valery. And questions, Alexander?
Is it possible to say something about possibility to non-spherical spherical symmetrical burst? For instance, when you have some special direction of burst and something like this from observational point of view.
You mean some anisotropy factor, or what? Here we computed only plane parallel atmospheres with local spectra, yes. And what kind of deviation of spherical symmetry you mean? Some due to rotation or due to some spots on the surface? What kind of asymmetry you mean?
Yes, it may cover a large part of surface of a neutron star, not spot, but nevertheless it may be.
You mean that only part of the neutron star could be accreted, could be heated due to accretion? Yes, of course, it's possible. It will be some additional parameter when we will compare with observations. Unfortunately, too many parameters.
More questions? And can I ask you about, there you have the spectrum. Maybe can you return back a couple of slides? This one, yeah.
This?
Yeah, one of those, yeah. It does.
Or this?
No,
or
later.
This?
Later. Let's stop. Next one, I think. Next one.
This one?
Next one. Yes, here.
I
I think this red curve is very interesting. You have additional flux at low energies and some additional flux at high energies, right?
So brighter.
So, yeah, it becomes much broader. So this atmosphere, heated atmosphere, it's very thin, like optical depth, I don't know, 5 or something, even less.
For electron scattering.
For electron scattering, yeah. So does it produce Bremsstrahlung?
Yes, of course.
This is the low energy.
This heated part of the atmosphere is optically thick for low energy photons, and of course he give some additional emission.
So this is Bremsstrahlung, what you see on the left, on the low.
Bremsstrahlung from this upper.
And this tail, high energy tail, you think it's just Compton scattering from the same?
Due to Compton scattering.
Okay. Okay. Good. At least I understand.
It's especially important for these models with low intrinsic luminosity. Here is accretion luminosity 50 times larger than intrinsic, and all of the photons arise here in the heated part of the atmosphere and comptonize it then and give this spectrum.
Okay, great. Okay, if there are no questions, let's thank Valery and